Good day, ladies and gentlemen. This is Mudau L, your tutor. So today I will be doing physics, grade 11 and 12 concept. And this is science clinic online extra lessons. So our main idea here is to let learners understand this simple concept that they fail to do it correctly in exams and also in their test, because they have misconception. There's a lot of misconception with regard to this concept of normal force. So we'll be doing this normal force in this video and in our next video. Today our focus is going to be on a horizontal plane. So before we can even proceed, we have to define this type of force, normal force. What is normal force? Normal force, we use big letter N to represent normal force. And this is a contact force. Let us look at the definition according to the exam guideline. So according to exam guideline, it says that is the force or the component of a force which a surface exerts on an object in contact with it and which is perpendicular to the surface, Okay, now I want us to underline the keywords. A surface exerts on an object in contact with it and which is perpendicular to the surface. So meaning that this force acts perpendicularly to the surface. It doesn't matter whether an object is on a horizontal plane or a inclined plane. Those who don't know a horizontal plane, I will show you not so long. So the object must be in contact with the surface. That is the key word. You have to know that for a normal force to exist, then the object must be in contact with the surface. Then there will be a normal force. And another thing you have to know is that normal force, it acts perpendicularly to the surface, or it forms 90 degrees with the surface. So today we are going to look at normal force on an horizontal plane. On a horizontal plane, it says that note that the following the normal force acts perpendicular to the surface irrespective of whether the plane is horizontal or inclined. So I will explain that later on. For horizontal planes, the only forces perpendicular to the plane should be the weight, number one, and the normal force. All other forces should be either parallel to the plane or at an angle. Should be either parallel to the plane or at an angle. Okay, then for inclined plane, we'll discuss that later. Now, I want to show you 3 cases on a horizontal plane. I want to show you 3 cases on a horizontal plane. Okay, now from the definition, it says that the surface exerts a force on an object that is in contact with. So let us have case number 1 here. I will use cases. Case number 1 here for horizontal plane. Case number 1. So for case number 1, let us draw an object. I will use a block, an object, and this object is on a horizontal plane. This is a horizontal plane. Now, according to the definition, the object is in contact with the surface. Good. Therefore, there is a force that the surface exerts on this object, which is called normal force. So I will use a free body diagram to draw the normal force. I'm just assuming this object is not moving, so it's just lying on a horizontal plane, and there is no friction. So this is the free body diagram for this object. Okay, free body diagram. So we're going to have a dot. This I would draw a free body diagram, use a dot. This is the normal force. Is the force that acts perpendicularly. Is the force that acts perpendicularly. So it will act in this fashion. Let me draw on the object here. So this is the force, normal force. Okay, now, if you remember, there are two forces that act perpendicularly to the surface on a horizontal plane. We also have the weight. The weight. These two forces are always at equilibrium. They are always at equilibrium on a horizontal plane. Actually, to be precise, the upwards forces, the forces that are up and the forces that are down, that point downwards, they are always at equilibrium. That is why the object will just move on the surface without going up and down, as such. Okay, let us leave that for now. This is the normal force, and this is the weight. So, according to universal law of gravity, weight is defined by mass multiplied by gravitational acceleration. Mass in kg multiplied by gravitational acceleration in meters per second squared. Therefore, if that is the case and these two forces are at equilibrium, normal force is equals to weight. And if that is the case, therefore, normal force is equals to mg, where m is the mass and g is gravitational acceleration. If we're dealing with s, then this g is going to be 9.8 meters per second squared. So m is just the mass of an object in kg. So this is case number 1 of normal. So let me show you case number 2 of when we deal with normal. So this time around, I will assume that the object is moving. Let me go to the next slide. So case number 2. Suppose we have an object here. The same object is in contact with the surface, and there is a force applied parallel to the surface. Here is the force. I'm assuming that this surface of ours is rough. Therefore, if the surface is rough, then we're going to have friction. So I will first draw the free body diagram. Just want to show you something. This is the free body diagram. This is the normal force. It always acts what? Perpendicularly to the surface. And this is the weight. Here is the applied force, our F there. And here is, I'm assuming that the object is moving, therefore it's going to be kinetic friction. We'll discuss this later on, but I don't see any misconception with regard to this one. Then you can see that these forces, as I said earlier, they are at equilibrium. Therefore, normal force will be equal to weight. And this is mg. So normal force is equal to what? Weight. So now we are going to case number 3. This case is very, very much important. Actually, most of the learners, they understand these two first cases. They understand that normal is equals to weight, which is mg. But in all other problems, they just say normal is equals always like that. And that is not the case. Normal force is not always equals to weight. So it depends on the certain problem. In some problems, normal force is equal to weight. And in some problems, normal force is not equal to weight. To be precise, normal force is equal to weight if the force applied on an object is parallel to the surface. So it's different when we look at this case now. Let us look at this case number 3. With case number 3, I want to show you something. This is F. You can see that is applied at an angle. And we have a rough surface. So I will first draw the free body diagram. Here, let me draw the free body and the force diagram. Here is the free body. This side, I will draw the force. Free body diagram for this case. This is normal. And this is weight. Of course, we're going to have friction. I will assume that the object is moving. And you can see we have F applied here. Then for a force diagram, force is more or less the same as free body. It's just that we don't use a dot. We use a small box. FA, FK, and weight. I hope you can see the difference between free body and the force diagram. So they're different. For free body, we just use the dot. And for force diagram, we use a box or a circle. We are also allowed to use this. Now, I want us to define normal force. Here, in this case, we cannot just say normal force is equal to weight. Why? Because this force, it has its component. It can be resolved into this force, which is FAX. So this is the horizontal component of applied force. And we also have the vertical component of applied force, which is FAY. So we know that FAX is defined by FA cos of theta, because it's the adjacent of our theta. Our theta, it must be here. And the FAY is defined by FA sine of theta, because it's the opposite of theta. FAY is the opposite of theta. Okay, now you can see that we have these forces here. Now the forces are 3. We have 2 pointing upwards and 1 pointing downwards. These forces are always at equilibrium, as I said earlier. Therefore, the sum of the two, FAY plus normal force, it must give us weight. Meaning that normal force now is defined by weight minus FAY So this is mg minus fa sine of theta. So this is how you should define the normal force for this case. And you can see that if you just say normal force is equal to mg, then you're wrong, because normal force is less than weight for this case. It's less than weight, because when you add the normal and the component of the force, you get weight. I hope it's clear. Then now let us look at the last case for today. Then I will show you some examples. The last case for today, case number 4. Case number 4. Now we are having a block, and let us still have a horizontal plane which is rough. And now here we have the applied force. We have the applied force. So let us draw the free body diagram for this case. So this will be the free body diagram. Normal force is always perpendicular to the surface. And weight, here we're going to have Fk. I'm assuming that the block is moving. So some educators, they will prefer to draw F in this format. So since we're using a tail-to-tail method, then we have to start it from here going down. So this is our F. This is our F applied. This is our F applied. Now, our theta is here. So the same with the previous case, this force has components. Let us have the first component, which is the FAX component. And we also have this component, the FAY component. Now, you can see that, as I said, that these forces are always at equilibrium. Hence, we are going to have the following. Normal force is defined by weight plus FAY. So weight is mg, FAY is FA sine of theta. So this is how we define normal force. This is how we define normal force on a horizontal plane. So let us look at some examples. I want us to look at some examples. I want us to look at some examples. Example number 1. Example number 1 is related to case number 1 and the case number 2. It says that the 10 kg block rests on a horizontal surface. Draw a free body diagram showing all forces acting on the block. So meaning that we are having a block of mass 10 kg just lying like that. So we are asked to draw a free body diagram, and we have to show all forces. Then let us draw the free body diagram. Remember, when you're asked to draw a free body diagram, you must label your forces. N for normal, and we have this one, weight W for weight. Some they use FG, still okay. Now let us proceed to the next question. It says that calculate the weight of the block. G is equals to 9,8, that is gravitational due to gravity on Earth, acceleration due to gravity on Earth. So weight is equals to mg. We are told that the mass of the block is 10 kg and the acceleration is 9,8. Hence, so 9,8 multiplied by 10 is 98. Is 98. So it's 98 newtons. Then this is the weight. And we know from case number 1 and 2 that normal force is equal to weight. Hence, normal is equals to weight is going to be 98 newtons. It's going to be 98 newtons. So I think this is a simple example. It's just a simple example that you can all do. But when we come to problems of this nature in the exam, so most of the learners, they forget these cases, of which that is why we are doing them. We are doing them so that you will always remember these cases. You will always remember these cases. Now, I want us to proceed to the following example. Example number 2. We are moving to example number 2. Example number 2. Let me share example number 2. This is example number 2. It says that 15 kg cement block is pulled across the rough floor with a force of 100 newtons, which forms an angle of 30 degrees with the horizontal. So draw a free body diagram. We're going to do 2.1 this side. So we're drawing a free body diagram and a force diagram. So we're going to draw a free body on the left. Then we'll draw the force on the right. Let us start by normal. You can see that this normal is an obvious case. And we have weight. And here we have F applied. We have friction. So with the force diagram, we have normal. We have a weight here. We have F applied. Then we have FK. Remember, you must label these forces. You must label these forces. So I will not label now, but you have to know that always you should label the forces. Let us move to 2.2. Calculate the normal force acting on the block. What must come in your mind is that this is case number 2. So if it's case number 2, the force there, it has what? It has components. The applied force, it has components. Let me show you here. You have normal, we have weight. So this is F applied. This F applied has components. So we have this component, which is FAX, and we have this component, which is FAY, meaning that you can see that normal force plus FAY is equals to weight. Hence, normal force is equals to weight minus FAY, which is mg FA sine of theta. So what is mg? M is 15, g we're taking 9,8 minus FA. What is FA? We are given 100 newtons, and the sine of theta. Sine of theta. So let us calculate this. Let us calculate this. Remember, sine of theta is 0,5. So we're saying 15 multiplied by 9,8. That is 147 minus 0,5. Oh, it's 0,5 multiplied by 100, sorry, which is 50. Which is 50. And the answer is just 97 newtons. So this is the normal force for this case. I hope you understand this problem now. Okay, let us move to our last example. Our last example for today. Example number 3. This is another problem that most of the learners, they fail to answer it correctly in the exam. So I believe you will get it right this time. I believe you will get it right this time. Okay, let us draw the free body diagram as the first question. So it says that the picture below shows a boy pushing a lawnmower of mass 22 across a lawn at constant speed. So when you find this word constant speed, you must remember Newton's first law. It simply means that the opposite forces are equal. The opposite forces are equal. So the object is at equilibrium. So applying a constant force at 35 degrees. There is no force here. A constant force of, let me add, of 50 newtons. Constant force of 50 newtons at 35 degrees. Now, draw a level free body diagram. Now let us draw a free body diagram. Up here, we are going to have the following. Normal force, you can see that normal force is always perpendicular to the surface. It's always perpendicular to the surface. Not like it's always pointing upwards. No, that's misconception of the definition. So we have friction here. We are not told that the surface is smooth, therefore there is friction. And this is our F applied, the force that the boy is applying on the lawn mower. Now, you can see that now we are having a force that acts at an angle, hence it will have components. We're going to have the horizontal and vertical component. We're going to have the horizontal and vertical component for this applied force. For this applied force. So here we have the horizontal one, and here we have the vertical one. Hence, normal force, you can see, is defined by weight plus FAY. This mg, F applied sine of theta. So what is M? It's 22, 9,8. What is FA? FA is 50. Sine of 35. Sine of 35. So let us press our calculator and see what we'll have. 22 multiplied by 9,8 is 215,6. Then we add 50 sine of 35. 50 sine of 35. Then we are going to have 244,279. 244, let me say to the nearest 2,28 newtons. So this is the normal force for this case. So thank you for joining us today. In our next lesson, we are going to look at normal force on an inclined plane. God bless you. Shalom.